Going over the Leetcode problem, making a large island. Level hard, solution is going to be in Java. So yeah, feel free to take a look at the problem description, which is going to be in the link below, and let's go over the solution. So this is a classic problem revolving around finding the connected components of the graph, right? This is the main pattern, of this problem, right? Because an island is a connected component, right? Okay. Okay. Now, so the high level solution, right, or algorithm has two steps to this problem. The first is that we need to find all the connected components of the graph, right? And then the second is we want to go through all the zeros in the graph, and for each zero, we see what connected components are adjacent to that zero, right? Okay. To that zero, right? Okay. And then if we flip the 0 to a 1, then what's going to happen, right? So all those connected components will be connected, right? We're talking about the adjacent connected components will be connected plus the flipped 1, right? Now that flipped 1 becomes part of that entire connected component. Now we need to update our result accordingly, right? So that's the general algorithm. Now there's a few details to take note of, which is that one, we need to use a visited matrix while finding the connected components to avoid iterating infinitely in a cycle, right? Because we don't want to visit the same cell twice. And then the second thing is that for each zero, while seeing which connected components are adjacent, we can use a data structure like a hash set to keep track of the IDs of the connected components already found to avoid double connecting, counting connected component, right? So another general takeaway is that in all of these sort of graph theory problems, right, oftentimes you're going to need to use data structures like a visited matrix or a hash set to avoid duplicate iterations or counts. Okay. Perfect. And now let's go over the time and space complexity, right? So time complexity, that's going to be big O of n squared, right? Because we need to iterate through every cell in the provided grid, where n is the n. Yeah. So remember the grid is n by n, right? So n by n or n squared, right? Now the space complexity is going to be O(n) squared as well, because we need to use a visited matrix, a matrix to keep track of this, to keep track of the size of the component, that each cell belongs to, as well as, and plus we also need a matrix to map what component each cell belongs to, and so forth, right? And so forth, right? So really, dimensions n by n, resulting in space complexity of n squared, okay? So with that being said, now let's write out the solution. Okay, so we're going to need to first define a matrix which stores the size of the component that each cell belongs to, and right, if the cell doesn't belong to a component, then we'll just we'll just technically say that the size of that component is 0, right? So 0 if it doesn't belong to a component, right? So we'll define a two-dimensional integer array, component sizes or matrix, right, equals to int grid.length, grid 0.length. So yeah, rows and then columns, right? Okay. And then we also need to have a matrix which maps each cell to what component it belongs to, right? So int cell components equals to new int grid.length, basically the same thing, right? Same dimensions. And then we'll need to have a flag to indicate what component a cell is in while we do our iteration. So int cur component equals to 0. And while we do our iteration, we need to use a visited matrix, which keeps track of the cells that we visited when we are finding the grid's components, right? So it's a two-dimensional Boolean array equals to new Boolean grid.length and then grid 0.length, right? Okay. Next, we're going to, so another, common thing in these graph theory problems is defining movements, right? So we can define movements using a 2D array representing essentially a list of vectors, right? So in this case, we can move horizontally or vertically, right? So we'll define that data structure, define the directions that we can go to from a cell. So int directions equals to new int -1 0 1 0 0 -1 0 1, right? That's going to cover all those horizontal and vertical movements. Okay. So next, we're going to what do we need to do? Yeah, we need to define the maximum component size, right? Int max component size. It's going to be default to 0, right? In the case that we can't find a 0 in that grid, right? Perfect. Now we can go through our iteration, right? So we're going to iterate through every element in the grid, right? So it's going to be a two-dimensional for loop. So for in I equals to 0, I less than grid.length, I plus plus, right? For in j equals to 0, now we're iterating. This outer loop iterates through the rows. Now we're iterating through the columns. So in j equals to 0, j less than grid 0.length, j plus plus, right? Okay. And so first thing is that if the cell is 1, it belongs to an island, right? And we only find the component that the cell belongs to if we haven't visited it yet, right? So if grid ij equals to 1 and visited ij, right? If the cell is 1 and belongs to an island, only the component that that the cell belongs to, we only find the component that the cell belongs to if we haven't visited it yet, right? Actually, to make things more clear, we'll just rephrase it to say if we haven't visited the cell and the cell is 1, it belongs to an island, right? So if we haven't visited the cell and grid at ij equals to 1, right? That's our condition. Then what we're going to do is we can execute a graph traversal. Let's use BFS. Pretty simple to implement. Execute a BFS traversal to find the component, right? So the component size, it's going to start out at 0, right? And then the current component ID, right? Yeah, we'll rename this to current component ID to make things more clear, right? So we're going to update the current component ID, so cur component ID plus plus, right? Because we found a new component, right? And then let's go through the heart of that BFS traversal, right? First thing that we need to do is we need to have a linked list of cells, essentially, which we're going to represent with, an integer array, right, of size 2, row and column, right? So this is going to store all the cells in the component, which is going to be equal to a new linked list, int, right? Next, we're going to need to create a queue, right, to store the cells that we want to visit. So queue equals a new linked list, int, right? And then we're going to start out by searching from the root of the component, or essentially the first element that we're going to start searching from is, the current cell that we're on, right? So q.add in new int I and j, perfect, right? And then while we still have cells to visit, right? So while the queue isn't empty, we're going to get the current cell we want to analyze. We'll just retrieve the row and the column so it's easier for us to access it, instead of always typing out cur cell 0 and cur cell 1. So again, if we haven't visited that cell, right, we're gonna first mark it as visited, right? Then we're gonna update our component size, right? Because this is another cell that's gonna go into our component, and then we need to add that cell, right, to our list of cells in that component, and then we're going to mark the current cell's component, right? Cell components RC, right? Yep, we defined that. Cell components RC is going to equal to cur component, right? And next, what we're going to do is we're going to figure out the neighboring cells that also belong to the component, right? So this is where the paradigm that I talked about, where we're using vectors to represent movements, really comes into handy. So for every direction in directions, we're going to compute that new cell, right? Simple vector addition. So r plus direction 0, updated the row. Now we need to update the column, direction 1, right? C plus direction 1, right? Next, we need to check that the new cell is valid, right? So it's within range, because there's going to be edge cases where you're on a boundary cell, right? A cell on the edge, and you can't, move further in a direction, right? If you're on the left edge, you can't move forward you can't move to the left, right? And that's going to make the column negative, right? So we have to check that the new cell is valid. So what are those conditions, right? Let's first check that the row is valid, right? Equals to new cell equals to 0, and new cell 0 less than grid dot length, right? So check that the row is valid, right? And then next we need to check that the column is valid, right? So check that the column is valid, right? So if new cell 1 is greater or equal to 0 and new cell 1 is less than grid at index 0 dot length, right? Perfect. And then yeah, we need to check that we have not already visited the cell, right? So if we haven't visited new cell 0, new cell 1, okay, and grid at new cell 0 and new cell 1, right, equals to 1, okay, right? Because we only want to visit cells that are 1. Otherwise, if it's 0, it doesn't belong to a connected component or our island, right? So if that's the case, we're going to explore that new cell. So we're going to add it to our queue, right? So yeah, this BFS traversal, I believe, should be done. Where's the while loop? Right, while loop terminates here, right? Okay, so BFS traversal is done, right? And then we update the max component size if necessary, right? So max component size, it's just we just take the maximum of the existing value for that variable and then the new component size, right? Okay, and then again, we're going to need to update the matrix storing the sizes of the component each cell is in, right? So for every cell in component cells, right, what we're going to do is component sizes at cell 0 and cell 1, that's going to equal to component size, right? All right. And with that, I think we can move on to the next step of the problem, which is 2, right? Go through all the zeros in the graph, and for each 0, see what connected components are adjacent to that 0. If we flip the 0 to a 1, then all those connected components will be connected, plus the flipped one. Update the result accordingly. Perfect. Yep. We can move on to that next step in our high-level algorithm. So yeah, so we're going to iterate through all the zeros and figure out the maximum island we can generate from the flip, right? So we'll define our result, right? The result that we want to return. So again, we're gonna go through every single cell in the grid. Can't use I and j again. So we'll define in r equals to 0, r less than grid dot length, right? R plus plus, right? For int c equals to 0, c less than grid 0 dot length, c plus plus, right? And so again, we are only allowed to flip zeros. Okay, so if grid rc equals to 0, right? We're gonna figure out what are the neighboring components from the current cell. So int we'll say max island size, right, equals to 1, right? Because we're flipping the because the maximum island size, it's going to start out from 1, right? Because we're flipping the current cell from a 0 to a 1, right? So yeah, max island size, it's going to be the maximum size of the island that we can create from flipping the current cell from 0 to 1, right? Okay. Next, we need to use a hash set, right, to store the unique components that we have already connected by flipping the current cell from 0 to 1, right? So hash set set integer unique components equals to new hash set integer, right? And essentially there's 4 cases, right? We need to check the top component, check the bottom component, check the left component, and check the right component, right? So actually I should rephrase that. We should check, if the above cell is in a component, right? If the bottom cell is in a component, if the left cell is in a component, and then if the right cell is in the component, and then expand the island that we're trying to create accordingly, right? So yeah, analyze possible component at top, right? Possible above component, right? So if r is greater than 0, right, because we need to check the edge case that r equals to 0. So we check that the above cell is actually in a component, right? So if grid r minus 1, grid c equals to 1, right, then what we're going to do is we're going to get the component that the cell is in, right? So in cell component equals to cell components, and we're going to reference that at r minus 1 column, right? R minus 1, because we're looking at the above cell, right? And if our unique components doesn't already contain the cell component, right, because we don't want to, double count it again, right? Then max island, or double count or double analyze it again, max island plus equals to component sizes at r minus 1 c, right? And then unique components dot add. We need to update this hash set so we make sure we do not visit it again, right? Okay, perfect. Now let's check the bottom component, right? Possible bottom component, right? So if r is less than grid dot length minus 1, right, then check that the cell actually is in a component, right? So yeah, we need to first see if the cell is in a component. So int cell component equals to cell components r plus 1 at c, right? Now if we haven't visited it already, right, so we check that by looking at our hash set unique components, right? Then what we're going to do is we're going to expand our island accordingly. So max island plus equals to component sizes at r plus 1 and c, right? And then unique components dot add cell component, right? Okay, perfect. And then we need to analyze the possible left component, right? Actually, I think I made a mistake here, right? If grid R minus C, um, I actually didn't make a mistake because it's just a redundant piece of code. Because here, right, where I checked that the above cell is in a component grid R minus at R index R minus 1, index C equals to 1, right? So by default, Java initializes all the elements in that 2D matrix to 0, right? So um, even if I even if the statement executes with grid R minus 1 C equals to 0, it's not going to do anything because component sizes at that cell is going to be 0, right? So um, yeah, let me make a note of that. So note that by default, all cells in 2D matrix, this is for Java, are 0. Okay. So yeah, we don't need this extra check. That's redundant. Yep. Perfect. All right. So now let's move forward. We're going to analyze the left component. So if C is greater than 0, then what's going to happen is, again, we're literally doing the exact same thing, equals to, yeah, I think this whole thing is just if R greater than 0, right? It's literally the same code. And then, yeah, we need to do the same thing for the right component. Yeah. A better programming practice would be to, factor this out into a function. We can do that after we see that the solution works. But yeah, so that analyzes all the 4 cases, right? So above, bottom, left, and right. So we've expanded the island starting from the cell in which we flip from 0 to 1 accordingly. And then we'll update the result, which is going to be math.max result max island, right? And then finally, we can return the result, but there's one quick thing that we need to do. So where does this, okay, the for loop ends here, right? So there's a one nuance that I want to mention, which is that if the result is 0, right, the result that we computed here is actually the maximum island size from the flip, right, from flipping 0, right? But if we, if flipping a 0 didn't actually end up, didn't end up creating an island to begin with, then we just returned the maximum component size out of all the initial connected components that we found, right? So this should more accordingly be named max component size from flip, right? So let's update that variable name, result max component size from flip, right? Max component size, where else is that? Okay, max component size from flip equals to 0, and then if not, max component, and if it is 0, right, we're just going to take the maximum component size from all the initial connected components that we found, and then if not, we're just going to return max component size from flip, right? So we'll run this code, see if it works. Looks like we, line 33, got some errors. Line 33, forgot a semicolon. Line 69. Dot class expected. Is that because of the previous error? No. Oh, there's a typo, right? If new cell at index 1. All right, now 71. Q dot add new cell. 149. 149. It says illegal start of from expression. Let's see. Equal to 0. Component size. Oh yeah, an extra colon. Yeah. Cannot find symbol cur component. Oh, new cell 1. Yeah, that's another typo. Cur component. So while the Q, oh yeah, should be cur component ID. Yeah, whoops. Let's run that again. Cannot find symbol, max island, plus equals to, it should be max island size, right? Line 118, yeah, max island size, max island size, max island size, right? Cannot find symbol, max island size. Perfect. Let's run this again. At index, if int, oh yeah, I made a dumb mistake again. Analyze possible bottom component, right? It is essentially the same code for all these cases, but we have to update the indexes accordingly. For this one, it's correct because bottom is row plus 1. Left component, it should be cell minus 1, right? And then right component, it should be cell plus 1. And then we need to update, this according, all the indexes accordingly. R minus 1, R minus 1, C, C, R minus 1, R, C, R plus 1, C, R, C minus 1, R, C minus 1. And then our right component is going to be C plus 1, right? C plus 1. Oh, right component. Oh yeah, it should be if C is less than grid at index 0 dot length minus 1, right? Yeah. All right, so successfully passed all the initial test cases. Let's submit it. And let's see. Yeah, accepted. Runtime beats 52.39% of users. Memory beats 53.99% of users. So yeah, pretty decent solution. It looks like everything worked. And yeah, in an actual interview, one thing that I would suggest would just be to like modularize this into a function. Or actually, you can. I mean, you could if you wanted to, but not too important, right? So yeah, overall, this is the solution, and hope you guys enjoyed the video. I'll be posting this code in the link below, as well as all my other solutions to Leetcode, and then I'll be posting the write-up for the answer on core. Appreciate it. Don't forget to like, comment, subscribe, and see you guys in the next one.